Assalamualaikum warahmatullahi taala wabarakatuh. So we are from Group 10. So first member for our Group 10 is Muhammad Adli Aiman bin Azhar, metric number AC 220106. And second member is Umi Najah binti Nordin, the metric number is DE 220090. And the third one is me, Haikal Iqbal bin Abdul Hadi. My metric number is CE 220093. So this is a data set description for our group. So the data set consists of a sensor reading that help train the model to predict accurate distance, and it contains three main columns, which is the first column is field of view, FOV angle, and the angle at which the Kinect sensor is capturing depth, and the next column is a Kinect estimate reading, which is in meter, and the raw distance measurement estimate by the Kinect depth sensor. And the last column is the laser measure reading ground truth. The actual distance measured using a high precision laser sensor which serve as our reference or target output. And before we start, before we train the model, we perform several pre-processing steps to ensure the data quality. So we have three things that we do, which is the first one is we clean the column name for clarity and consistency. The second one is we drop missing value to avoid error and bias during training. And the last one is normalize all features using min-max scalar, which scale the value to a range between 0 and 1. This thing all is important because of we have to ensure all the input contribute equally to the training process and improve model performance for both model 1 and model 2.
Hi, Assalamualaikum. My name is Muhammad Adli Aiman and my number metric is CE220106. And today I will develop and design ANN model using Google Colab with the data given. So the data given, which is Kinect FOV angle, and then Kinect reading and laser reading. So this data we convert to the graph using NNN model, and we show in the Google Colab. So first, this data we must save into my drive, and it's easy to Google Colab detect the file into the drive. And this is the data. And second, we go to the Google Colab. Okay. First of all of the code, we type the from Google Colab and import drive. So in this part of the code, we working with fly stored in the Google Drive through the Google Colab. And then second code is import OS. We use the file path which is Google Colab notebook that saved into the Google Drive, and we type the OS list dir to detect the file. So in this code, the file that Google Colab has found. This row, we are loading an Excel file from Google Drive using pandas. Okay, first we import the pandas library, which is powerful for handling data, and then we set the path to the Excel file stored in our drive. So this is our file address, and then we use the data head to show us the first few rows of the data so we can get a quick look at the content. And this is our first row of the data. Okay, for this row, we here used to use the display function along with PD data frame to show the entire data set in a clean, colorable table format. So this is more readable and interactive than just printing rows, especially for a larger data set. So this is full data.
Assalamualaikum warahmatullahi wabarakatuh. My name is Umi Najah binti Nordin and my metric number is DE220090. So I would like to present and explain about the first model, first we will go through with the coding. So for the step 1, which is data processing, in here we import all necessary libraries for data processing, visualization, model building and optimization. So next, load the data set. So we load the Excel file using pandas, which is the things that we extract is 2 features, 2 input variable and target, the value that we want to predict. So next, in the scalar and feature scalar is the range of 0 and 1, which is this will help neural network to coverage faster. Next, in the data splitting, we split the data into 2, which is training for 70% and validation for 30%. For step 2, model development. So as we learned before, for the image processing, we have 3 stages, which is input, hidden layer and output. So in model development, in the hidden layer, we use first layer, we have 32 neuron. Second hidden layer is 16 neuron and output layer 1 neuron with linear activation. Next, we compile all the information. Step 3 is evaluation. We evaluate the model on validation data using MSE and MAE. Step 4 is prediction and visualization. We make prediction on the validation set. So for the graph 1 coding, which is for training and validation loss, we write encoding. We write coding to plot loss over epoch for both training and validation to diagnose overfitting or underfitting. While for the graph 2 is for actual versus predicted scatter plot. And for the graph 3 is about line plot of actual versus predicted. So for the first graph, which is about training and validation loss, as you can see in here, y-axis is for loss, x-axis is about for training epoch from 0 to 50. Red line for training loss, blue line is for validation loss. So as we can see in the graph, the very first epoch, the model start with high loss, which is near 2.7, which drop sharply within the first epoch. Then for both training and validation loss, stabilize very quickly near 0. So in here, there's no sign of overfitting or underfitting, which suggests the model coverage faster. So next is predicted graph. So for the y-axis is predicted output value and x-axis is sample index. So in here, the spread of point appears random and uncorrelated, which might indicate poor model performance, especially if actual value are not closely alike. So next is for the line plot. So the line plot in here is only for actual. So y-axis is output value, x-axis is sample index. So in here, the value are very high, ranging from 1 to 7, which is not normalized. So that's all from me. I will pass to the next presenter. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum. My name is Haikal Iqmal bin Abdul Hadi. My metric number is CE22009 So I would like to present and explain about our model 2 for our group. So first thing first is step 1, which is what we do in step 1 is data pre-processing. So the first thing first is we import a essential library for a data for manipulation, scaling, modeling, and visualization. And then we load the data set from a Google Drive and extract features related to the Kinect sensor reading and the target laser measurement. And Kinect sensor reading and the target laser measurement is actually our title for this assignment. And then we normalize the data. So how we normalize the data is we use a min-max scaler to normalize the input features, which is crucial for stable and a fast neural network training. And then the next step, the last step for step 1 is we split the data into two sides, which is training is 70 and validation is 30. And we set is a fixed random seed to ensure the reproducibility for step 1. And then we move to the step 2, which is model development. And what we do in the step 2 is we define a deeper multi-layer perceptron, MLP, model called model 2. This is model 2. And then we have 164 neuron in the first hidden layer, followed by 32, 16, and 1 is the final output. And we active the ReLU function for linearity activation for this regression output. And then we compile the model using a stochastic gradient descent, which is SGD, and we optimize with the learning rate of 0.01 and the momentum is 0.9. And we train the model for 50 epochs with batch size 16, validating performance on the health of validation loss. And the next step, which is step 3, is evaluation. So what we do in the evaluation is actually we evaluate the model performance on validation data to obtain loss and mean absolute error metric. Simple step in the step 3, and then we move to the next step, which is visualization, which is step 4, graphic comparison. So what we do in step 4 is we plot, the first thing first is we plot the training and validation loss curve over epoch to monitor convergence and check for overfitting or underfitting. This is very crucial for this, for how we can get the result for model 2, which is we need to know whether the result is overfitting or underfitting. And then we create a scatter plot comparing actual laser reading versus predict value to visually inspect prediction accuracy. And then the last thing is we use a line plot to show trend and alignment between actual and predict value across sample. And then the last one, which is a final comparison, and we print the validation loss and mean absolute error for model 2. So after we run, we got the result for our model 2. Like this is a training and validation loss for model 2. This is the epoch. We got 50 epoch. And actual versus predict for model 2. The vertical one is a sample index, and the horizontal is the normalized output. So your horizontal is the sample index, and in the x-axis is the normalized output for model 2. This is actual versus predict. And then the last one is a line plot for actual versus predict. So this is our result for model 2. And that's all from me. Thank you.
Okay, we go to the methodology part. Okay, this is training and validation loss. So this is the model 1 and this is a model 2. Okay, the model 1, the loss decreased rapidly in the first few epochs and stabilized later. Second, the training and validation loss converged smoothly and no sign of overfitting nor divergence between training and validation. However, final loss remained high, indicating underfitting. So the model 2, MAE decreased consistently across epochs. And final MAE is 4.16, which means on average prediction are off by 4 meters.
and this level of error is too high for precise robotic application. So the model shows basic learning behavior, but the height loss and MAE indicate limited performance. Architecture may be too shallow or the target was not normalized. And okay, this is the actual versus predicted graph. So this is the model 1 and then this is the model 2. So the scatter of red dot and green dot were plotted randomly, this indicating poor model accuracy. And we go to the line plot, actual versus predict. So this is the line plot model 1 and then this is the model 2. Okay, the model 1 validation loss is 19.266, which while MAE 4.16, and then for the model 2 validation loss 0.022 and the MAE is 0.112. Okay, so the conclusion, in our comparison between model 1 and model 2, we found that model 2 produced less error in terms of both mean absolute error MAE and mean square error MSE. This is because model 2 has deeper architecture while more layers and neuron, allowing it to learn more complex pattern in the data. Both models were trained on normalized input features using the same optimizer SGD, but model 2 increased capacity helped it make more accurate prediction, resulting in lower overall error during validation. This shows that a well-structured deep neural network can significantly improve performance when handling non-linear regression tasks. So that's all for me. Thank you.